Hi guys, for this video we're going to look at a few practice questions on the application of Kirchhoff's laws. The first one seems to be very basic in the sense that we're just looking at the use of KCL, and in the second one we have this where we have voltage being introduced here to see what else is involved there, and then we have this network and we'll see how to work it out. So let's start with the first one. So for this question, we're being asked to find the branch currents I1 and I4. So let's find them. I1 is the branch current passing through this line, while I4, where is it? I4 is right here, the branch current passing through that line. So let's remind ourselves of what KCL is. So KCL, Kirchhoff's current law. What does it state? It states that at any junction, the current entering the junction will be equal to the current leaving the junction, or at any junction, if we were to sum all currents entering and leaving, this should be equals to 0. So of course we'll take currents entering to be positive currents and currents leaving to be negative currents. Based on that concept, let's see what we can do. So we're going to start with this junction here, and what we have to do is we have to identify all the currents entering and leaving. We see that our I1 enters that junction, so according to Kirchhoff's current law, we have I1 entering, so we'll keep it positive. Then we also have I2 entering, so I2 entering, we'll also keep it positive, plus I2. Then lastly, we have the current through this branch. So that current is leaving, so I know it is leaving because of the direction of the arrowhead there. And that current is a 2 amp current, so have minus 2 amps. This has to be equals to 0, which reduces to I1 plus I2 is equal to 2 amps. So this is our first equation. We don't know what I2 is, so keep it like that. Next up, let's come to this one here. So for that node or for that junction, we have 3 currents. I2 leaves, then I have 3 amps leaving through this, and then I have 7 amps leaving through that. So by Kirchhoff's current law, here we're seeing that all 3 currents seem to be leaving. So you have I2 leaving, so you have minus I2. Then what else? We have 3 amps leaving, so we're going to have minus 3 amps. Then we have the 7 amps also leaving, so we're going to have minus 7 as well. So this has to be equals to 0, that is the last one. So for that junction, I2 goes to the right, becomes positive. This will be minus 3 minus 7, which becomes minus 10. So this tells us that I2 is negative 10 amps. Well, knowing I2, notice that we can now bring I2 to our equation 1. Equation 1 says that if we added I1 with I2, this should give us 2 amps. This is equation 1. But since we now know I2 is 10 amps, negative 10 amps, we can now say this is plus negative 10 amps is equals to 2. From here, I1 is now minus 10 here is equals to 2. And finally, I1 will be 2 plus 10. Of course, this is just I1 is equals to 12 amps. So we have found what I1 is. Now, in case you're wondering what the negative here implies, so if a current comes out to be negative, the only thing it implies to your circuit is that if the direction of the current was inserted to be this way, a negative current implies that the correct direction of current here is actually that direction. It doesn't mean that you should change the orientation. It's just you keep it exactly the way it is. As long as you maintain the use of current to go in this direction, then you must use the negative 10 amps. But should you decide to wait, I want to use the positive I, and change and say you take the direction to be that way, it will now mean that for this node, you have to rewrite the expression, and so that now for this node, you take I2 to be leaving. That is the only way you'll be able to use the 10 amps as a positive value. Otherwise, as I pointed out, you don't have to change that. You can keep the direction of I2 to be this way, but you just have to be using negative 10 amps. Okay, so that sorts out that node. So now we go to this node here. So for this node, what are we seeing there? The 7 amps enters, so you have plus 7 amps that enters. I3 leaves, so we have minus I3. And then what else? We have I4 enters, so you have plus I4 is equal to 0. So those are the only three. 7 enters, I3 leaves, I4 enters as well. From here, we see that we have I can say I4 minus I3. Okay, let me keep 7 on the left side, take I4 to the other side, so that I3 becomes the positive one, I4 the negative one. This will be equal to 7. So I can keep this as my equation number 2. So here I can find I4 unless if I knew I3. But look at what happens when I come to this node. I see that for this node, I actually find I4 directly, because for that node, the 2 amps in this line enters, so I have plus 2 amps. The I4 and the 4 amps are leaving, so I have minus I4 minus 4 amps is equals to 0. From here, I4 goes to the right side, giving us positive I4 there when you rearrange, and then this will be 2 minus 4 there. So this has gone to the right, becoming a positive, leaving 2 minus 4, which is that. So when you simplify, you get I4 being equals to negative 2 amps. So we'll keep it like that. We'll give it with a negative value, because here the orientation of I4 is given to be in this direction. So as long as it is in this direction, we have to present our answer as a negative. So present it with that negative. So the question did not ask us to find I3. They actually wanted I1 to I4. So we will have to find all the currents here, I1, 2, 3, up to 4. So we already have I4. We have found I4. And earlier we found I2 here as well. And then we also found I1. So only I3 is now left. But from equation 3, which is this, we can now just insert the value of I4. So what is our I4? So we now have our I3 minus our I4 had the negative, that was negative 2 amps. So you have negative 2 amps here, and then this is equals to 7. So you see that this is now I3 plus 2 is equals to 7. So that finally we have I3 is equals to 7 minus 2, which is going to give us a 5 amps. So there we have it. All the currents they wanted. I1, we had 12 amps. I2 was negative, and that was negative 10 amps. Then I3 is 5 amps. And finally I4, we had negative 2 amps. So these are the currents that they wanted for this question. Now let's look at the second question here. So for this one, we now want to find V, which is the voltage drop across the 12 ohms, and IX. IX is the current passing through this circuit element here. So how do we do that? Here, we're going to be seeing the use of Kirchhoff's voltage law. So I'm picking Kirchhoff's voltage law here because we are seeing voltage drops being indicated here. So how are we going to use Kirchhoff's voltage law? So in Kirchhoff's voltage law, all we have to remember is that the sum of all voltages around a closed loop has to be equals to 0. So how does that work? If you were to loop around any closed loop, the sum of all the voltages has to give us a 0. So sum of all potential drops has to reduce to 0. But how do we use that? Let's start from the bottom here. When looping, if you find a circuit element negative first, consider the drop there to be negative. So we're going to have negative 10 here. And then when you continue, we find a resistor. Usually, when you find a resistor, to get the potential drop there, use Ohm's law, multiply the current passing through it by the resistance value. But for this case, you see that we can actually just go with the voltage V. And let's just take this to say it's what gives us the voltage value V. So, and we find it positive first, we'll keep it plus, and then we'll just put a voltage value V. And when we continue, we see that here we find this resistor. And for this resistor, we find it positive first. We find that circuit element positive first. And here as well, we see that we're not given the resistance value. Instead, we're given the potential drop there. So go with that potential drop. No need for us to have IR, I mean. So go with plus the potential drop. Since this is the last circuit element in this loop, so end there and say this has to equal to 0. From here, we see that V will have to be equal to, when the negative 10 and the 4 go to the right, we'll have positive 10 minus 4. We see that V has to be equals to 6 volts. So we have found V to be 6 volts. Now we want to find Ix. To find Ix, we're now going to use Kirchhoff's voltage law, but we're going to do it this side. Now, the same concept. When we start, we find negative first of this circuit element down here. So finding that minus first. And the value there for the voltage, again here, this is where we only have the voltage, so this will be minus 4. When we continue, we now find the 16 there, the 16 volt drop across that element. And this time we're finding positive first, so we're going to have plus the 16. So that's a voltage value, we'll go with the voltage. So when we continue, we now find this dependent voltage source, and we find it positive first, so we'll have plus here, and this is going to be plus 3ix. So this has to be equals to 0. That is the last circuit element in that loop. So you see that here everything else is known except Ix. So you can work out this to find Ix. So let's find Ix. So when we sum this, we get 12 here plus 3. Ix is equals to 0, and then from here we have 3Ix is equals to negative 12, so that finally we find Ix to be equal to negative 4. Since Ix is a current, that's negative 4 amps. Now let's look at this question. So here, of course, the circuit looks weird, but it's still very basic. You still use the same concepts. What do they want us to find? For the network shown, find the current, voltage, and power associated with the 20 kilo ohm resistor. The 20 kilo ohm resistor is here. We want to find the current passing through it, the voltage drop across it, and the power dissipated by that resistor. Or, the power used up. So how do we do that? Well, here it's very basic. We want to get the current passing through it for starters. How do we do that? So we can even start from this side. So we can start with just a basic loop. So again, we can start with just looping around this circuit. So what happens? So it doesn't matter whether I loop through the 5 as well, or I loop all the way just up to the 20. This is Kirchhoff's voltage law works with loops, regardless of how you look at it. So if I'm looping going all the way to the 20 there, what is happening? So we see that here, I won't necessarily do the loop here. So I don't really want to do the loop here for one simple reason. If I tried to start by looping, I will have this. It is a current source, a dependent current source. So there'll be a question mark on how much voltage is coming from here. So instead, what I'll do is, since what I want to find first is the current passing through the 20, imagine if you knew the actual current coming from this source, then you can just use current division to understand how much current goes towards the 20 kilo ohm. If you knew how much current goes there, then it means that you can easily get the voltage drop, the power, and you're done. So to find how much current is actually coming from this source, notice that the current value depends on what V0 is. So here, the current value depends on V0, and V0 is coming from this side. So let's find V0 first. So for this part, we're going to start with looking at this circuit here, or this part of the circuit, and we see that to find V0, V0 is the voltage drop across the 10 kilo ohm. So how do we find that voltage drop there? By Ohm's law, voltage, because again, this is current, or this current, the 5 milliamps, goes to pass through that 10 kilo. So if I wanted to find the voltage drop across the 10 kilo, which is V0, it will be the current, which is 5 milliamps, multiplying the resistance there, which is 10 kilo ohms. So in the end, notice that I haven't tried to convert the units, because I see that the milli and the kilo are going to affect each other such that they'll basically just cancel each other there. You can still convert to just the amp and the ohm, but it's still, this is going to reduce to just a 50 volt. So V0 comes out as a 50 volts. Once you have the value of V0, you can now understand how much current is actually being sent in this line by that dependent source. So you have 0.01 V0, and this is what will be equals to 0.01. Our V0 is 50. So when you multiply, you get 0.5. You get 0.5 amps. So this voltage controlled current source is actually sending 0.5 amps of current. Now that 0.5 amps at this junction, it's going to be split so that part of it goes towards the 20. That is what we want to find, the current towards the 20 kilo ohm. So to find the current going towards the 20, we will now use current division. By current division, the current going towards the 20 kilo ohm will be equal to, you know how current division works, it's the other resistor on top. So this is going to be 5 kilo divided by 5 kilo plus 20 kilo, then multiplying the current they're sharing. These are all sharing 0.5 amps. So let's simplify this to find the value. So here we'll add what needs to be added. This will be 5 over 25 multiplying 0.5. So this is just 1 over 5 multiplying 0.5 amps. And this will give us 0.1 amps. So the current that ends up going towards the 20 kilo ohm resistor will just end up being 0.1 amps. Notice that I didn't try to convert the 5 kilo and the 20 kilo ohm resistors to ohms, because in the end, you're going to have a kilo ohm and a kilo ohm down, so they're just going to cancel out. So this is how much current goes towards the 20 kilo. So we have solved the first part. Now, to get the voltage drop associated with that 20 kilo ohm, so the voltage drop across the 20, how do you do that? By Ohm's law, voltage drop across the 20 kilo ohm will be equal to the current passing through the 20 multiplying the resistance of that resistor. So the current passing through that is 0.1 amps multiplying the resistance value. So this is going to be 20. I can even take it to ohms. So that's 20 kilo ohms, just 20,000 ohms. So when you multiply this, you get 2,000. You get 2,000 volts. So of course 0.1 by this is in ohms, so you get 2,000 ohms. Or you can say you get 2 kilovolts. So this is how much voltage will be dropped across that resistor. The last part was to find the power associated with that resistor. Power is voltage times current. So since we know the voltage is 2000 volts, the current 0.1 amps. So yes, the current there was 0.1 amps. So when you multiply this, we see that the power here is going to be 200 watts. Okay, just make sure you go through the math here, do the numbers, just make sure that we haven't made any mistakes. All right, so that's it for this question. Let's wait for the next one.